Hello, it's my pleasure to present this case study on applying systems engineering principles to design and implement an automated warehouse. In our rapidly evolving industrial landscape, the integration of automation has become both a necessity and a challenge. This presentation will walk you through how a holistic, structured engineering approach can help manage complexity, achieve operational excellence, and align technological innovation with strategic goals. We will explore not just technical execution, but also stakeholder engagement, risk mitigation, and long-term maintainability. Let's begin with a broader view. The warehousing industry has undergone a dramatic transformation over the past 30 years. Originally characterized by labor-intensive processes, manual picking, and high error rates, warehouses today rely on sophisticated technologies. RFID tagging, barcode scanning, and machine learning have revolutionized how we handle inventory. Companies like Amazon and DHL have set new industry standards by adopting high-throughput systems like automated storage and retrieval systems, ASRS, autonomous mobile robots, AMRs, and predictive warehouse management systems. These advances have reduced costs, minimized human error, and allow operations to scale with demand, especially during peak seasons. So, how do we build such systems? Traditional engineering methods often fail to manage the complexity of integrating mechanical, electrical, software, and human subsystems. Systems engineering, by contrast, focuses on the entire life cycle, from concept to decommissioning, ensuring that every component aligns with overarching goals. We use structure models like the V model to link requirement definition to validation, enabling us to detect issues early and iterate effectively. Additionally, we employ modular design strategies, risk management frameworks, and requirement traceability tools to track dependencies, interface constraints, and stakeholder expectations. Our project was with a leading national retailer aiming to overhaul their distribution network. The goal was not just to automate, but to future-proof their warehousing operations to handle growing e-commerce demands and support traditional retail replenishment. Technologies involved included ASRS towers for high-density inventory management, robotic picking stations for precise order fulfillment, AMRs for mobile logistics, and a central warehouse management system, WMS, for real-time control. Physical space constraints and tight deployment timelines added to the challenge, making systems engineering indispensable. The first step in systems engineering is needs analysis. We engaged a diverse group of stakeholders, executives, warehouse managers, IT teams, maintenance staff, and even end customers. Each had unique priorities. Executives focused on ROI and brand value. Warehouse managers wanted faster throughput, fewer bottlenecks, and high uptime. IT teams required seamless integration with existing ERP systems. Maintenance crews emphasized reliability and ease of servicing. Finally, customers demanded accurate, fast delivery and hassle-free returns. By translating these varied inputs into structured, measurable requirements, we created a blueprint that truly reflected the needs of the system. With clear needs established, we explored multiple architectural concepts. 3 options emerged: a fully automated system, a semi-automated system relying on human-machine collaboration, and a hybrid-phased approach. Using weighted decision matrices and simulation tools like Monte Carlo analysis, we compared capital costs, scalability, implementation risk, and workforce impact. While the fully automated system promised speed, it came with high risk and cost. The hybrid model, by contrast, allowed phased integration and staff retraining. It proved the most balanced and practical choice for our clients' needs. Once the hybrid concept was selected, we defined the system at a high level. Modularity was key. We designed components to be replaceable and upgradable without requiring major redesigns. We mapped spatial layouts, defined interface points, and outlined safety zones. Key performance indicators included throughput targets of 5,000 order lines per hour, accuracy rates below 0.1%, and system uptime of 99.9%. Compliance with OSHA and ISO 10218 Part 2 safety standards was mandatory. This phase helped align expectations and set the stage for detailed engineering work. Next came detailed system design. Mechanical subsystems were modeled using CAD tools to determine exact layouts for conveyors, robotic stations, and AMR paths. Electrical schematics ensure power distribution and fault tolerance. On the software side, we separated WMS logic, robotic control, and human-machine interfaces into layer components. OPC UA protocols facilitated interoperability between vendor systems. We also defined procurement specs. Robotic arms with specific payloads and cycle times, AMRs with low limits and battery specs, and conveyor motors rated for peak load conditions. Audits were verified and documented in design reviews. Even well-designed parts can fail when integrated. We adopted a phased integration strategy, building subsystems in stages and testing them progressively. AMRs were tested in isolated corridors before full deployment. APIs were validated to ensure consistent data exchange between WMS, robotic pickers, and operator dashboards. Cybersecurity was another concern. Given the use of IoT-enabled devices, we conducted penetration tests and red teaming exercises to fortify our systems against digital threats. Interface control documents govern every interaction, eliminating ambiguity during this critical stage. We approach V&V methodically. First, we validated individual components like robotic arms and WMS modules. Next, we assemble and tested subsystems like AMR fleets and conveyor ASRS interfaces. Finally, we executed full system simulations using digital twins, modeling scenarios like peak holiday demand, power failures, and partial system outages. These simulations helped us identify performance bottlenecks and system limitations. Acceptance criteria were co-developed with stakeholders to ensure they reflected real business priorities. Treating V&V as a continuous process rather than a final hurdle ensures long-term quality. Before going live, we ran a pilot test in dedicated 10% section of the warehouse. This test mirrored real operations, standard picking, replenishment, reverse logistics, and exception handling. KPIs like AMR uptime, picking accuracy, and recovery times were rigorously monitored. Interestingly, some challenges like minor inefficiencies in AMR traffic only became apparent during this phase. Ergonomic issues at robotic stations also led to design changes. These insights proved invaluable in refining our systems and reducing the risk of disruption during full deployment. Full-scale deployment was handled through a phased rollout. We divided the warehouse into sectors and brought each online sequentially. This allowed for real-time adjustments and reduced learning curve friction for operators. Key processes like receiving and shipping were temporarily rerouted to maintain business continuity. We also conducted intensive training covering everything from WMS dashboards to emergency shutdown procedures. Live operational KPIs were monitored continuously, and adjustments such as modifying conveyor logic were implemented as needed. Automation changes the way we approach maintenance. We developed a proactive strategy that combined preventive, predictive, and corrective measures. Preventive tasks included regular inspections, sensor recalibration, and software updates. Predictive maintenance was enabled by telemetry analysis, detecting anomalies in battery voltage, vibration patterns, and motor temperature. Spare parts inventory was digitized and vendor contracts ensure rapid response times. Continuous training kept our maintenance teams updated on tools and protocols. This measure guaranteed minimal downtime and long-term sustainability. Managing complexity was a defining theme. Technical systems from different vendors had to communicate flawlessly. Organizationally, we coordinated multidisciplinary teams from mechanical engineers to IT personnel. Operationally, we maintain warehouse functionality during system upgrades. We adjust this through modular system design, rigorous ICDs, and phase execution. Shared dashboards, regular team meetings, and systems thinking workshops foster alignment and rapid issue resolution. Risks are inevitable, but how we manage them determines success. Our risk register was dynamic, updated weekly. Each high-impact risk had an owner and a mitigation playbook. We simulated risks using scenario planning and Monte Carlo analysis. For instance, if the AMR fleet failed, we had manual fallback procedures. If network latency rose, the WMS had offline caching. By integrating risk control into the workflow, we remain agile and avoided catastrophic failures. Stakeholder communication was continuous and tailored. Executives received monthly briefings highlighting ROI, milestones, and strategic risks. Managers got detailed readiness and training reports. Workers participated in town halls and hands-on system demos to ease anxiety to build confidence. Feedback mechanisms, surveys, suggestion boxes, open office hours enable a two-way dialogue that improved both morale and implementation outcomes. Looking back, 4 lessons stand out. First, early and frequent stakeholder engagement is non-negotiable. Second, modular and flexible design enables adaptation without chaos. Third, training is not peripheral. It's core to transformation. Fourth, systems thinking, considering interactions between people, processes, and technology. It's the most powerful tool for navigating complexity. These lessons are applicable not just to warehouses, but to any large-scale transformation. In conclusion, this project proved that technology alone isn't enough. Systems engineering provided the discipline, foresight, and adaptability needed to succeed. We increased throughput, cut costs, improve accuracy, and build resilience into our operations. Perhaps more importantly, we position the organization for future growth and innovation. Thank you for your attention. I welcome any questions you may have.